Let's keep cracking on with these questions. We're starting here with define acceleration. We've done this many times before. So either just write out is the rate of change of velocity, or you could do rearrange v equals u plus at and define your terms. Right, B, super tanker cruising at initial velocity of 6 meters per second takes 40 minutes to come to a stop. Constant deceleration. Calculate the magnitude of the deceleration. So the magnitude of the deceleration is going to be equal to the change in the velocity divided by the time. So we've got a quarter there with a 10 to the minus 2 thrown in. So that would be 2.5 times 10 to the minus 3 meters per second squared. Calculate the distance travelled in that 40 minutes. So that would be the average velocity multiplied by the time, of which they've given us all of these things. So the distance will be 3 times 2400. So that's 7.2 kilometers. Sketch the variation of distance traveled with time as it decelerates to a stop. Right, so we need it to go through 7.240, which is around about here, if that's at 7.2. And the gradient needs to be decreasing here. Because the velocity is decreasing. Remember, the velocity is the gradient. We're going to end up with a zero there, zero velocity, so it's going to be flat. We want to be doing something like that in a continuous curve. The student repeats one of Galileo's classic experiments from the 16th century. Trolley going down the slope with bells. Number of tiny bells are hung above the ramp. You release it from the top. It rings the bells as they're going down. You keep doing this and adjust the position of the bells until the time between successive bells is the same. So the bells are ringing at regular intervals. So the distance is going to be increasing, but the time is staying the same. State what you can deduce about the motion of the trolley as it travels down the ramp. Well, what we can deduce and what the student can deduce are two different things, because they're not telling us how far apart all of these bells are. If you're the student and you've made these measurements and then you're calculating all of these things, then we can deduce that there is constant acceleration. That is the thing that we're going to be looking at, because you'll be putting this into essentially s equals a half at squared. That's what we're going to be putting in to this, because we're measuring distances and times, and then it'll tell us something about the acceleration. We can't deduce this. I mean, it has said, what can you deduce? Well, we can't because we haven't been given the distances. But the student, if it said, what could the student deduce? Then yeah, go for it. Right, the positions of the bells are unchanged. The mass of the trolley is increased. This heavier trolley is released from rest at the top of the ramp. State and explain the observations made by the student for this trolley. Well, there isn't going to be any change. So we want no change on this. We're going to be getting the same acceleration going on. The reason, same acceleration. The reason we're getting the same acceleration is that we've got the force is proportional to the weight, and which is then proportional to the mass, and the acceleration is then going to be, well, it's also proportional to the mass times acceleration. So proportional to mass is equal to mass times acceleration is what I mean. What am I writing out here? So we've got F equals ma, but F itself is proportional to mass. So therefore the mass is going to cancel on both sides, and the acceleration is independent of mass. Okay, I kind of waffled a bit at the beginning, but we're wanting to show that the force here is coming from the weight. So force comes from weight. The weight is proportional to the mass. So when we plug that into our F equals ma, the masses are going to cancel. So the acceleration is not a function of mass. That is the thing that's going to be important with this. It's going to be a function of the angle of the ramp. That's the thing that's going to come up, because we've got on this, if you think of what's going on, we've got weight going down there, that's mg. So the component that we've got of this down the slope is we've got an mg sine theta going down there. That is our component down the slope. That is equal to mass times acceleration. So we cancel those. So the acceleration is a function of the angle of the ramp and the acceleration due to gravity. So yes, that's that one. Here we have a car of 1,200 kilograms traveling at 18 meters per second along a horizontal road. So it's not actually this picture here. This is on a horizontal road. Constant braking force of 3,600 newtons brings it to rest. Calculate the magnitude of the deceleration. Okay, so we're going to do F equals ma. We've got F is 3600. Divide that by the mass, 1200, gives us the acceleration, which is 3 meters per second squared. So that's the magnitude of the deceleration is 3. Calculate the distance traveled by the car during the deceleration. So the distance is going to be the average velocity multiplied by the time. It's clearly going to take 6 seconds to stop, because we're going from 18 down to 0 in blocks of 3. So we're just going to have 6 times 9, which is 54 meters. So quite straightforward there. The same car travels down a slope at the same speed. It's got the same braking force. Explain whether the distance travelled by the car before it stops is greater than, smaller than, or the same as your answer to B. So it's going to be greater than. The reason, I suppose there's 2 different ways you could put this. You could say from a force point of view, we've got a component of the weight going down the slope, because we've got the weight coming down here. So we're going to have a component of the weight which is down the slope. So the net force is less. Our resultant force is lower. So that's one way we could go because of this component of the weight. Or we could talk about energy rather than force. So we could say that the work done here, I mean, that's got to take away the kinetic energy of the car plus the GPE, which is going to be added in because we've dropped down a particular height here as we're going down the slope. So we have to do more work with the same braking force, so we must have a greater distance. So the work done has gone up, the force is the same, so therefore the distance has got to go up. So we've got 2 different ways of talking about that one. Right, now we've got in part D, many cars are fitted with global positioning system devices, GPS. Describe how geostationary satellites are used to track the location of cars on the Earth's surface. Right, okay, so we need to say there's a number of key points you need to put on this. So we got radio or microwaves. They're the ones that are used by the satellites. So these are sent by the satellites to the car. So we've got satellites here. You have to have more than one of them. We can then measure calculate distances. So you calculate distance from the delay time, the time of arrival, multiplied by the speed of light, because these are all electromagnetic waves, so they're all going to move at the speed of light. So if we've got a time times a velocity, we're going to get a distance. That gives us distances from each of the satellites. So what we need to be careful with here is we're using trilateration. A lot of people say triangulation, but trilateration is getting position of an object by using distances from fixed points. So if we got distances from the satellites, we use trilateration in order to say where the car is. This is different to triangulation, where we're using angles, as suggested by the name, triangulation. So we've got the, sometimes you can add the 2 of them together. So you know, if we've got maybe with mobile phones as well, you could combine the 2 with a car and then have you know, masts on the Earth or something where you're looking at particular angles between things. This is usually what goes on when you see it in, I don't know, crime programs on TV, and they're triangulating between mobile phone masks. So they're using angles from fixed points towards where the mobile phone is. Trilateration is using distance. Right, this looks like we've got a projectiles question. We've got a small block of wood held at a horizontal distance 1.2 meters from a metal ball. Metal ball is fired horizontally towards the block at a speed of 8 meters per second. The same instant the ball is fired, the block is released, falls vertically under gravity. Right, okay, so we've got all of this. The ball collides with the block, air resistance is negligible. Show that the time between firing the ball and colliding with the block is 0.15 seconds. Right, so that's just going to be 1.2 meters. So yeah, it's going 1.2 meters. It's doing it at 8 meters per second. So we're just dividing that out. So that is going to be 1.5 divided by 10. So that is 0.15 seconds. So that's exactly what we want for part A. Calculate the vertical distance h fallen by the wooden block when it collides with the metal ball. Okay, so they both drop by the same amount. So how much does something drop in 0.15 seconds? It's starting from rest. So we're just going to have S is 1/2 times GT squared. So we just have to type all of that in. Let's get this on. We've got 9.81 times 0.5 times 0.15 squared is 0.11 meters. So 11 centimeters, 0.11 meters. Explain briefly why the metal ball will always collide with a wooden block, even if the speed of the ball or the horizontal distance is changed. Right, so I suppose we need to put in two things here. They're both have same vertical acceleration, and they both have the same initial vertical velocity, i.e., which equals 0. So yeah, if we got those the same, they're always going to hit each other at the same point. Draw a line from each unit on the left-hand side to the equivalent unit on the right-hand side. Okay, so we got energy here, joules. We've got a force times distance, so work done is force times distance. We've got watts, which is joules per second, and then we've got newtons. So hopefully this is going to be something that looks like mass times acceleration, and lo and behold, it is. This question is about estimating the pressure exerted by a person wearing shoes standing on a floor. Estimate the weight in newtons of a person. Well, I don't know, let's take someone who's around about 70 kilograms, and we'll multiply that by G, so 9.81. So whatever that comes out as, 9.81 times 70, close enough. So around about 686, so let's say 700 newtons. Let's just go with that, rounding up. Didn't really need to use the calculator, did I? If I was going to round up, just 70 times 10. Estimate the total area of contact in square meters between the shoes of this person and the floor. Okay, so let's say that, I don't know, someone's foot is going to be, well, let's say it's a foot long, so it's about 30 centimeters. And it's maybe 5 centimeters wide. I don't know really. So let's say we've got 30 centimeters by 5 centimeters, and then you've got 2 feet. So let's say that's about 300 centimeters square, something like that. Oh, we want this in square meters, actually, in all of this. So that's going to be 0.03 square meters. Hence, estimate the pressure in pascals. So that is the force divided by the area. So we've got, what's that, 700 divided by 0.03. 700 divided by 0.03 equals 23 kilopascals, thereabouts. So yeah, It's just seeing if you can make some sensible guesses on what the size and mass and weight and such like of a person is, and then going through some basic calculations. Right, you should be getting used to these definitions by now. We've got to define a vector quantity. So here we're saying it's a quantity that includes both magnitude and direction. So quantity, I don't really need to write this out. So, but anyway, with magnitude and direction. Figure 1.1 shows graphs of velocity v against time for two cars, A and B, traveling on a straight level road in the same direction. So they start side by side at time t equals 0. Describe the motion of car A from t equals 0 to t equals 10 seconds. Right, so we'll split this up into the two obvious bits then. So we'll say t equals 0 to what's that, 4 seconds. We can say it's got positive velocity, positive constant acceleration. So this is a positive increasing velocity, might be a better way adding that in as well, because we've got this constant acceleration. And then time 4 to 10 seconds, we've got a positive constant velocity, and we've got zero acceleration. So yeah, we're just trying to put a positive or negative on these things, and then whether they're changing or not. That gets you quite a lot of marks. Just put in those. Calculate the distance travelled by car A in the first 4 seconds. So in these 4 seconds, we've got an average velocity of, what's that, 17. So we've got 17 times 4, which is going to give us 68. Right, so that's 68 meters. So that's covered that bit. Use figure 1.1 to find the time at which both cars have exactly the same velocity. The time at which both cars have the same velocity and the time at which they overtake. Right, so they've got the same velocity at whatever that point is, which is really hard to read off there. It looks like it's 1.2 seconds, maybe, if I've read that okay. So at 1.2 seconds, we've got the same velocity. I was already jumping ahead of myself, thinking they were going to ask when they overtake. So when does car A overtake car B? Oh, well, that's going to be relatively straightforward then, isn't it? Because we're going to want to have the same amount of time again past this. Because the distance is going to be the area under the graph. So B gets that far ahead, so we need to take that amount back again. And because this is a straight line, it's going to have to be at 2.4 seconds when A overtakes. So we don't even have to bother getting into calculating areas and things like that. We've just got a nice symmetry in the geometry of all of this.